So my name is Ryan Hipple. I work at Schell Games, and at Schell Games, I'm a senior game engineer, and I'm a terrible artist and an even worse writer. At Schell Games, this is okay, because we're surrounded by a ton of people who are really good at these disciplines. And I found that one of the things that, as engineers, we can do are build game systems and tools that enhance the stuff that our art team can actually create. In this session, Empowering Content Creators, I'm going to talk about some of the things that we've built for our current project that allow us to squeeze the most art out of our artists and the most words out of our writers. I'll give you some background on the project we're working on right now. Bill talked about it a little bit. It's called The World of Lexica. And it is a game that is meant to be distributed to kids in schools. They're going to be running this game on a tablet, and it ties curriculum content for English and language arts into an interactive game experience. And this focus here is very strongly on storytelling. So the goal is to drive more of an interest into reading and more of an interest into getting into this English and language arts curriculum. I would describe the game as Kingdom Hearts meets English class meets maybe Never-Ending Story. We also want to showcase the characters from these books very well. There's some really cool characters that you can encounter in English class books, and one of our goals is to make sure that we show them off as these really cool, engaging characters. And finally, we want to push creativity. We want to make sure the kids feel like they can be creative, and this leads towards creative writing. So we have lots of customization features in our game to encourage this. There's some interesting things about this project from the perspective of development. For Schell Games, and I think for a lot of Unity projects, this is a very large team. We're looking around 50 to 60 people right now working on this, and this is our largest project to date. And the timeline is also very, very long. We've been working on it somewhere around 1.5 years right now, and we've got a lot of time left in development. And this has its fair share of challenges. Right now, we have a single animator for this, and I mentioned there's a strong focus on storytelling and on showcasing characters, so this is a challenge. We also have only a few character artists, so in order to get all of our stuff through the pipeline, we need to work out some solutions there, because we have so many characters. And finally, a game about storytelling, we have a ton of story content. Story content and quest content is what drives the goal of the game. Kids are going to be reading content and then using that to learn about the quests. So to solve those challenges, and we have a lot more challenges in the project, but not that I'm going to address in this talk, we've created two systems, the character augmentation system and the vignette system. The character augmentation system is the thing that when a player first starts the game, they're able to select a base character. And what I have is the three base characters are a cat-hound hybrid type character, a hippogriff, and a yeti. Here they're pictured with some of their augmentations. Once the player picks one of these characters, we want them to feel like they have the creative power to do anything they want. We want them to feel like they can be anything that they want, no matter how absurd or ridiculous that thing might be. So the goals of this system, when we started the project, were to make sure that we could encourage some deep character customization. And when I say deep character customization, I mean more than just the hat you see pictured here, but we want to be able to add wings and tails and other things to the character that actually add life to the character and are animated. So when we add wings to the character, the wings need to flap and the tails need to wag. And it needs to perform well on a tablet. We're shipping on a handful of specific tablet models, so performance is certainly an issue here. Also, we need an efficient pipeline. I talked about some of the constraints we have on the art team side. We need to be able to get content through that pipeline very, very quickly and be able to iterate on it. And that leads us into having previewing and debugging tools that any discipline can really use. And we have built previewing and debugging tools that will run on the tablet so that our art team can view how everything looks on the final hardware without having to wait for the next build. So the features of the system that we have built are that we dynamically create a skeleton by combining all of the bones of the FBX files that we encounter. So if an artist wants to create a new augmentation, they create an FBX in Maya that has the mesh data and all of the bone data, and they export it into a special hierarchy structure, or folder hierarchy, into our project. From there, they click a button, and we parse through the folder structure and build up all the data we need to create a character. The requirement here is that each augmentation needs to have a single bone that has the same name as a bone of the body, and this tells us where these pieces fit together. Once we combine the bones and create a new dynamic skeleton, we have a single skin mesh renderer that wraps around that skeleton. That helps us out a little bit with performance because we're just going to have one skin mesh renderer and won't have the overhead of animating multiple skin mesh renderers. So since we're adding a new bone structure to each one of these augmentations, one of the things that we can do is have special animation, as I mentioned. If this cat here is playing his run animation without any augmentations, you'll see him run across the world. If we add the wings on him, while he runs, we want the wings to flap like he's trying to give himself an extra boost. So those wings have an animation that is parallel to all of the animations that we can play on the body. And we can sync up and have those play to make sure the wings look lifelike. In those animations, we can throw off events to play sounds. So when our cat walks without any wings, you hear footsteps. If you add the wings, you'll see the wings flapping, and you'll now hear wings flapping. So each augmentation is a fully contained package that adds extra data to it, and that data is packed in the animations. We can also throw off particle effects in the wings as well, or any other augmentation. And you can see this electrified collar around the cat's neck, so we have some static effects that we allow for in the augmentations as well. So the way that we do all this at an overview level is we start with a list of assets. I mentioned that our art team provides us with FBX files into a special folder structure. In the game, all we need is a list of these FBX files in order to begin generating a character. So we start with this list of assets, and then we're going to build this character in 2 phases. The first phase, we're going to load the asset at that path. We're going to build the final skeleton so that we know what to skin in the next phase. We're also going to count up some key data from each one of these, and build the skeleton, there it is. And we're gonna load up some key data from each one of these assets so that we can allocate memory for the next phase. So we're gonna count the verts, we're gonna count the normals and the triangles used for each one of these meshes. Then we can allocate the memory that we're going to use in phase 2. Phase 2 is where we build our mesh. We know exactly how many verts we need from the previous phase. We apply the skinning to the bones that we created in the previous phase, and then we just pop our materials on there. To jump into a little bit more detail on phase 1 here, so here's an example. If I have a cat character with a body and a tail, how do I generate a character from this? So we first encounter this body FBX file, and we're gonna load the file and inspect some metadata on this. So we're not going to actually look into the individual vertices here, but we're gonna see how many there are. And we're gonna keep a running count of all of our verts, and this lets us know at the next phase how much memory we need to allocate. And when I say verts, I also mean our normals, our UVs, and the count of our triangle list, and any other data we're using in the mesh. Next, so down here is where we're keeping track of the count of all the verts we have. Next, we're going to start building up our skeleton. So this is the first augmentation that we've added, the body. The body is just like any other augmentation, it just happens to be the first one. So for these 30 bones, we step through each one of them and copy them over into the scene as we begin building our character. This is the skeleton of a cat without a tail, because the tail's coming next. We also need to keep track of something here, the bone map, which is not significant on the first augmentation. You'll see its significance when we get to the tail. So when we encounter the tail, we again count the amount of verts. We see that there's now 840 verts involved in this. This means that we can allocate the memory we need for phase 2 at this point. And then we see that there's 5 bones in the tail. So we can copy the bones over just like we did for the body. If you take a look here, you can see that there's only 4 new bones to this structure. That's because this 5th bone here is that yellow bone, that's the pelvis. The artists create these models with this one bone in common. We call it the merge bone or the common bone. And the body already had a bone named pelvis. So when we're building up the tail and we encounter that bone, this tells us we can discard the copy of the pelvis bone on the tail and instead reparent all of the tail's bones onto the pelvis that exists on the body. One of the things that is interesting about this is we can then transfer our skin weights from all of the verts around the pelvis bone on the tail. We can transfer those skin weights to the pelvis on the body. This is interesting. If you're familiar with how skinning works, generally each vert keeps track of 2 to 4 bones that influence it for animations. And it keeps track of those through their index, the bone index. So if we're going to change the bone indices, we need to keep a map of where they're going and where they came from. So the bone mapping here for the tail represents bone 0, which is the pelvis, is no longer bone 0. It's now, say, bone 5. It was the 5th bone built. And then the subsequent bones are now not 30, or they're not 1, 2, 3, and 4, but 30, 31, 32, 33. So at this point, we have our skeleton, and now we're ready to build up our mesh to skin the cat. Here, we need to keep track of our vertex offset. That's that extra field that I added there, and this is important. Similar to how we keep track of our bones and how their indices are changing, we need to keep track of that with our vertex so that we can rebuild our triangle list successfully. For people who aren't super familiar with how the mesh data works, we have the vertex list. Each vertex is essentially just a bunch of points in space. And then the triangle list defines how we draw lines between each of those points to form triangles to form the mesh. So for our triangle list, we would say draw a line from 0 to 1, 1 to 2, 2 to 0, and that gives us our triangle. We're building a mesh out of separate mesh data, so our vertex indices are changing. Our vertex indices are changing, so we need to keep track of that offset and know where they're going. So here, again, the body, the first thing we encounter, it's pretty simple. We can copy the mesh data over, but we need to update the vertex offset. Now when we encounter the tail and begin copying this into the one skin mesh renderer mesh field, we start our triangle list count at 800 instead of starting it at 0, and this lets us successfully build up the model. At this point, we would put together our materials on it as well. I am ready to jump into a demo of this augmentation system. I mentioned ensuring that we have, there it goes. Making sure we have tools for our content creators to see their stuff in game. And this is one of the scenes that we have. So this is a simple scene that lets, any time we have an update in one of the character models or we add anything to a character model, you can see it in this scene. It's called the Curioso scene. The Curiosos are the name of our player characters. Over on the right, we have a list of all available augmentations, and on the left, we have a list of all available animations. So once something new comes in, you can create a character and watch it all work. So here's a cat just playing as a simple cat, no tail. He blends between all his animations, and let's see what he looks like if we add a standard cat tail to him. Oh no, I can't see it on this monitor. There we are. If I generate this, there we are with a cat tail. If I were to find this guy on the scene, we also wrote a little component that lets us view bones, which is super useful for debugging this when writing it. You can see that he now has one skeleton combining everything, so he's a single skin mesh renderer. To give you something a little more interesting, I'm going to throw those wings on, and I should warn you that these are not final assets, so I apologize to the artist watching. And you can see that these wings will play their flap animation when I run to make it look like he's got some extra energy in him when he's running. We can play animations and see how they interact with all of the augmentations we have on the character. So if I play the bow animation, you can see that everything works as expected. I'm going to put an end to this demo and jump back to the presentation. This is a system that we built that gives our animators and our character artists the freedom to test and build content. But we have a lot of other people in the team that we need to make sure that they are able to freely test and build the content themselves. So this is where we built our vignette system. And this is essentially our cinematic and dialogue system. The goals of this system from the beginning were to allow it to display text. So if I have a conversation with somebody, we want to be able to see text. The game, again, focuses on storytelling, and it's meant to inspire kind of an interest in reading. So being able to read, test, and test reading comprehension with how they follow through into the quest is very important for us. So we need to display dialogue text and also have selectable responses so that I can have branching in my conversations. And the branching does not only have to be based on my response into a conversation. We can branch based on other game variables. So if I talk to character X and then go to talk to character Y, my conversation path can go down a different route because of that. And we also need to make sure we can animate the camera and the characters, which puts a little bit more stress on that tight bottleneck of the animation pipeline. But it's very important for us to showcase the book characters, and we can do this very well by putting really cool animations on them. One of the most important requirements of our vignette system is that it be extensible. I mentioned the long timeline of this project, several years. In that time, it just wasn't possible for us to fully understand the scope of the game and the goals of the game from the very beginning. So having a system like this where we know dialogue is going to be in this game, having a system where we can add features to that dialogue somewhat seamlessly was very, very important. For all the things I've listed here, I'm sure most people can think of one very brute force solution to solving all of these, and that's just to do it with code. And in our first pass, we did just that. So our engineering team, as Bill mentioned, we write C# and compile it into DLLs. In order to do all the conversations with the characters, we had our design team writing JavaScript files, and that defined all the conversations, the camera moves, and everything like that. The way we put it together was we had a single class defined in interaction with each character. It was a mono behavior. We threw it on the character and said, when I talk to him, display this text pointing to a localized file, then this text, and then move to this camera angle and so forth. This ended up creating excuse me, a ton of code duplication, and worse than that, a lot of bugs. We didn't want to have our design team and our writers spending so much of their time trying to debug these issues. And I think most importantly, it was just the poor use of time for writers. Not all of the design team has a computer science background, and we just didn't want to force everybody to learn this in order to do pretty much my job as a programmer. We want them to do the thing that I really am bad at, is write, because they're really good at it. So in order to solve this, we took a more data-driven approach, and the data-driven approach we call it the vignette graph. And the vignette graph is a directed graph of nodes. You can see here we allow for branching and also loops, which was important in allowing conversations to return to previous steps. This is essentially a state machine, and we allow for one active node at a time. So only one node here can be active at a time. And when it's active, it performs an action. And once that action is complete, either the user performs an action, does something, or just whatever the prerequisites for that action are satisfied, it will pass control to a child node. It's responsible for selecting the next node that gets control, pass control, and optionally pass data to the next node, which lets us have the graph be a little bit more dynamic. Of all of those nodes, the first one that we built, and probably the most important one, it's when you're playing the game, the thing that you can actually pick out as a different node in the graph, it's the smallest player observable chunk. We call that the vignette interaction node. And that is, if I talk to a player, we display an animation, a camera angle, and some text. Every time that camera angle changes, every time that text changes, that's a different vignette interaction node. This is how we do our camera cuts. And also change up the dialogue. So these are made up of a cinematic action and dialogue. The cinematic action is the animation component of this, and they get a little bit complex. We allow for animations on several characters in the scene. All of these start simultaneously. So Lumen, who's a character in our game, this is where he would play his stand-up animation, and as soon as that's complete, we queue up his standing idle, his standing cycle. This is important because if we have dialogue, we don't automatically advance. We wait for the player to click. So we need Lumen to be doing something in that time, otherwise he freezes. The enemy will play his runaway animation at the same time. He's off screen. We don't need to loop anything. And one of the key things here is the stage animation here. Right now, this is defining the camera angle. It has a lot more power than that, and I'll get into that in a detail. I'll jump into detail in that in a bit. The dialogue is very straightforward. We have a speaker, the thing that they're saying, and optionally have responses. If I don't specify dialogue, we will play the cinematic actions, all of those animations, and once all the animations are complete, we'll automatically advance to the next node in the graph. Likewise, if I don't supply any cinematic actions, we'll play the dialogue and all animations will remain as they were before we entered the node. So to jump more into the cinematic actions and the dialogue system, the animations we use here, we have, as I mentioned before, one animator on the project, and it makes the most sense for us to keep him working in Maya as much as possible. It's most efficient for the team, and he does his best work when he's in Maya. So we needed to make sure all of his animation work could be done there. And we ended up creating two different types of animations that we use in vignettes. The first one are the character animations, which is kind of straightforward. It's when you have a skin mesh renderer deforming with transforms. And these are, we built several kinds of these, generic ones and specific ones. So the generics are a standing idle animation, or a walk cycle, or a sitting idle animation. These are things that can make sense in a lot of different contexts. And the specific animations we made here are some of the more costly things that we have in our game are like the specific animations of if two characters are getting into a fist fight and we have choreographed movements. We'll have specific animations that we'll probably only ever use in one context. Other than the character animations, the important thing from the stage is we can have our character animate what we call this prefab called the stage. The stage is a prefab that has a handful of transforms. That's really all it is. And our animator can define where all of these transforms are to control a bunch of different objects in the scene. The objects it controls are the camera. So our camera control comes from this stage, and it's not attached to a particular character or anything like that. And this lets us reuse different pieces of these interchangeably. This also has a special node that lets us fade the camera to black. The stage also has a transform for the player character that lets us move the player character around. And one of the cool things about this is if our animator animates the player character node to move from point A to point B, while the character moves, he'll automatically run through the game code that plays his running or walking or trot animation, so he'll appropriately run to that position. Also, for the stage, we have several marks for actors. So each character, once they're taking part in a vignette, we refer to them as actors in that vignette. And those actors have marks they need to assume on the stage. These are marks that our animator can animate on this one simple prefab. And the way we do this, or this allows us to frame a shot. So as soon as a vignette begins taking control, all of the actors are plopped onto their marks in the stage. So the camera has them exactly where he wants them to be. And if he animates those marks to move around, the characters will move with. So by animating just one simple stage prefab, we can use the existing generic animations. So have the mark move from one side of the stage to the other, and then play the walk cycle on the character. Once he's done, play their standing idle or their angry idle, and that lets us mix and match these. The stage animations take very, very little time to create, so in order to ease some of the stress on our character animation pipeline, we favor the stage animations and then mix in the pre-made generic character animations that we've already invested time in. So in order to keep our animator in Maya as much as possible, there are some challenges that we encountered. Our level creators stay in Unity as much as possible, because that's where they're creating the levels. And our animator often wants to make these special animations that interact with pieces of the environment. If I have a character that's leaning on a table or running down a hall and the camera needs to navigate around complex parts of the environment, it gets very difficult to do that in Maya without context. So originally we had lots of iteration on, oh, this doesn't look right, it goes through this wall. We found a quick solution around that, which was we created a tool that exports an OBJ, an aggregate of a bunch of objects in the scene. So somebody can select, I don't know, 10, 20, 100 objects in the scene and export them as one giant OBJ file. That OBJ file can be imported into Maya and then used as a frame of reference for all the animations. So they'll line up when they're leaning on a table, or the camera will smoothly go down this hallway. OBJ exporters are relatively simple. If you just do a Google search for OBJ exporter Unity, you'll find a ton of results for that. We also have a preview scene, much like the character scene I showed you earlier. We have a scene that lets us preview our vignettes, so it doesn't need to load up the full level that they're in. It just puts them in a scene with a nice grid on it and shows you the cinematic portions of it. And a debug view. So this is a graph of nodes, as I showed you before, and when you're on the tablet, we have an interface that lets you open up and view the vignette graph as it's played out so far. So you can see all of the nodes that you traverse through and your current node and see what all of the options are down the line. You can also hardwire a path on the vignette in case you need to debug a certain path without wanting to set all the variables correctly to make it down that path. There's a ton of other nodes, and this ended up becoming mostly a visual scripting system, kind of accidentally. All of the other nodes that we added in order to expose this functionality to the design team, all it really took for us was extending vignette node and defining what happens on enter. And once we do that, we can expose that functionality to the design team. The file format for these is another interesting thing. We are currently using a third-party backend to store a majority of our data for our game. And that made things a little bit tricky, but the important part of this, most of the details for that are outside of the scope of this talk. We export all that data to XML, and then we force it back into our game through parsing that XML into scriptable objects. I'm a big fan of using scriptable objects wherever possible. If you're not familiar with them, they're very much like a prefab saved into your project view instead of into the hierarchy, and they can have public fields and things like that on them. So the scriptable objects are saved out, in each vignette node is one scriptable object. So a graph can be made up of a bunch of different files. At the editor level, we have a an inspector that allows us to edit this vignette graph of scriptable objects. It isn't the tool that we use right now for our production vignettes, but I use it all the time when I'm adding a new feature and I want to create a debug vignette to test that feature. So all of our vignette nodes being scriptable objects creates the problem that we have like 50 files for a single vignette graph. In order to solve that, we wanted to get one file per vignette. When I commit to source control and I edit a single vignette, it's very useful to just commit a single file instead of 50 files. It's very unclear when we have a ton of different files that have been changed. So the command assetDatabase.addObjectToAsset, that actually lumps all of the files into one big file. And it's kind of cool if you look at that in a text editor, how it looks almost like a prefab with a bunch of different components on it. But we do that to collapse all of our scriptable objects into one file to make things much cleaner on source control. And it also means that you can't accidentally delete one of the nodes in the graph and break everything. I wanted to demo the vignette system with the time that we have left here. And I'm going to show you the debug scene that we've built for that. Let me switch to the vignette scene. So this is a tool, once our animator or the design team has created a vignette graph, they can open up this scene and start playing the game. You can see it's obviously in a debug environment. It's not a very pretty environment. But if I click on one of the vignettes that I want to preview, where's my inspector here? Oh. So if you can click on this, and if I click play, it will begin playing the vignette that I have selected. Normally in the game, we require all of the characters to be in the scene, but for this special scene, it will instantiate everything. All the characters here are moving around on their stage. The camera's moving on the stage. If he were in the scene, he'd be on a pedestal, so don't mind that. If I open the vignette graph, this is the interface that we have visible on the tablet and also obviously in the editor. Here's some of our dialogue text. I can click one of these options to jump to the next node. But by clicking through this, I can see all of the vignette interaction nodes. Those are the blue and green ones that we've traversed so far. They didn't have dialogue, so they just played animations and then proceeded. They also will fire off music, fire off some more animations, set some variables, and here we are right now. We come to a branch. So if I were to select, not a lot of room on the screen. If I select the top one here, you can see that it's going to highlight that top two-shot in red. It switches to the two-shot, plays the standing cycle on the character, and displays some text, and this is the localized string for that. I'm going to collapse this and zoom through this thing a little bit. Oh, the other thing I wanted to show you is the ability to hardwire these vignettes. This tiny little button here, I don't know if you can make it out from, yeah, you can. It changes one of these lines to green. This lets us hardwire the path of a vignette. And by doing that, if one of our branches happens to be on a variable of, did I talk to this person, 2 hours ago in gameplay, and I don't want to go and set that variable, I can just hardwire the vignette. So I'll make this one take path 1. So even if I click path 2, it's going to go up there and select that path. Continuing on, we have a bunch of other nodes that we would encounter, including this one. Oh no, I lost it off the top of the screen. That's unfortunate. I will stop the vignette and turn that off. The other tool that we built to allow our animations to come together very cleanly, since everything is coming in as different pieces of animations, we don't have one big animation that controls everybody in the scene. We wanted to make sure we had a way of previewing everything together and setting special keyframes. So if I switch to my project view and select what we call our action library, and this gives us our special editor for that action library. This is what our animator looks at when he's setting up the interactions on a vignette. So you can see mark 1, 2, and 3, the characters that are on those marks. So these are the people that are located in the scene that are going to be jumping to the marks that have been animated. And then down here we have a list of all of the animations, all the cinematic actions that have been specified for this vignette. I'll click on the intro, and let's again try to manage this screen space. If I click on this play, which I kind of ripped off the top of the Unity bar, it will play through the animation and stop. And if I scrub through this, we can scrub. And the interesting thing about this is that it's scrubbing through the animations of multiple actors at once. And this is where our effects team and our audio team can add keyframes. So if I right-click here, I get a keyframe that I can say, play a stage effect or play a sound. And that's where we can click and drag that to mark exactly where we're going to be for the next, where we want that sound effect to play off. So that wraps everything up. I have a very small amount of time left for questions. Do I have any time left for questions? 5 minutes left for questions. OK, that's great. If I don't get to answer your question, I'll be around the conference, or you can grab me, or you can send me an email. Please use the microphone because the room's a little big. Yes?
Hi. Are you guys still using the legacy animation system?
Currently, we are. We started this project with Unity 3.5, I believe. And the legacy animation system at the time, you hear right now, they added the ability to throw effects. We're using that because of the abilities that we need in our game. Also, with lots of our characters being quadrupeds, there weren't as many benefits to transferring over to Mechanim.
OK, thanks.
Anything else? All right. Thank you.